Okay, today's video is the continuation of this Pearson Edexcel International A-Level Unit 2, which is on waves and electricity. In part 1, I went through the electricity as well as the multiple choice, but I hadn't gone through the waves questions. So I'm going to focus on the questions I didn't do. So the real focus is on waves. Okay. Right, so if you haven't watched the first part, it's in the same playlist where you find this. Go back and look for it. And for those of you who request certain videos, make sure you go onto the home page and look at the various playlists which are there, and see if there's already videos on the unit that you're revising for. I'm doing them as fast as I can, but remember I'm also working full-time. So thanks for watching, sharing, liking, and hopefully you're already subscribed. Okay, so the first question that we didn't cover is question 11 after the multiple choice. Okay, so question 11, where are you? Okay, so that's the end of the multiple choice, which we went through. Here's question 11. So question 11 is about de Broglie. So this is de Broglie, the wavelength of electrons. So believe it or not, what you were taught were particles also exhibit wave-like properties. So they're giving you the velocity. And in your data sheet, you will find that the mass of the electron is provided. It's about 9.11 times 10 to the minus 31 kg. Okay? Once you know the mass of the electron, you can use the de Broglie equation for lambda. Let's just change the color to blue. Lambda for the electron will be h, which is Planck's constant, which is also on the data sheet, divided by the momentum of the electrons. So basically a faster moving electron will have a smaller wavelength, and a smaller wavelength allows you to probe material more easily. So basically the smaller wavelength, you should equate the smallness of the wavelength with the resolution that you can get down to. Okay, the more detail you can see. All right, and the wavelength of electrons, as you'll see, is much lower than the wavelength of light. So you put the Planck's constant, which is 6.63 times 10 to the minus 34, also on the data sheet, divided by the mass of the electrons, so divided by 9.11 times 10 to the minus 31, and the velocity they've given you in the question, 3.6 times 10 to the 7. And when you do this calculation, I've already done this to save time, it will give you the value of 2.02 times 10 to the minus 11. That's 3 significant figures. But you'll notice the data provided is 2 significant figures, so you should just say 2.0 times 10 to the minus 11, 2 significant figures, is sufficient. Okay? So that will get you the marks, and the marks then is 1 for working out the momentum. Yeah? So you could just do the momentum separately, which will be the bottom. So you get 1 for working out the momentum if you do that in a separate stage. 1 for putting the numbers into the whole de Broglie equation, so top and bottom, and 1 for getting the answer. Yeah, as I've done. They'll probably accept 3 significant figures as well. Okay? Here's the mark scheme. Next question, question 12, is about solar cells. Okay, so solar cell, they've given you the area in centimeters squared. So you've got to change the area into meters squared before, so don't get tricked by that. The battery will only charge, it says, when the power input to the solar cell is greater than 0.8 watts. Okay, it will charge then. Okay, so we got to work out if the power that we get is greater than 0.8 watts. That's what they want us to do. Okay, you've got to deduce whether the battery will charge if they tell you that the intensity of light is 750 watts per square meter. So there's an equation where the intensity is defined as the power in watts divided by the area in meters squared. So we know the area, yeah? We already know the area here. So put that into meters squared and we know the intensity. So all you've got to do is to make P the subject and multiply the intensity by the area, yeah? And you should get, you should figure out whether it's above 0.8 watts or not. So 750 times the area in meters squared, so 6.4 times 10 to the minus 2 times 10 to the minus 2 to convert from centimeters squared to meters squared. So that'd be times 10 to the minus 4. Okay? So once you do that, you will see that the power that you can produce with that intensity, P, remember to always put your equation down. Don't throw numbers on the page. It's an examiner's nightmare having to figure out what you're doing. Okay, so first show the equation you're using. Yeah, it doesn't take you long. And then the clarity will gain you marks in the exam. And this comes to 0.48 watts, and therefore you say power is insufficient. Okay, because it's less than 0.80 watts. Okay, and you'll get the final mark. I was meant to do that in blue. Power insufficient, power calculation. 3 marks. What's the third mark for? Working out the area, no doubt. I'm guessing. Let's have a look at the mark scheme. Yeah, so 1 for, yes. 1 for the comparison, 1 for the use of the equation, 1 for the answer. Okay, so putting the numbers in will get you 1 mark, getting the right answer will get you 2nd mark, and comparing it with 0.8 will get you the 3rd mark. Hope that makes sense. There are alternative ways using the 8, looking at the area you need. Yes, I think that's what they're telling you here, is if you can work out the area needed using the 0.8 watts, yeah, or working out the intensity you needed. That's an alternative way of doing it using the 0.80 watts, but I prefer the method of using the intensity provided and telling the examiner that you know that it's insufficient. Okay? To me, it's more logical doing it that way. Okay, the next question we've done before. So it's in part 1 of the video because it's mainly to do with electricity. So I'd gone through the electricity questions. So you can go back and have a look at question 13, which I've explained in the first part of this run through. Question 14 I haven't done, and it's using a diffraction grating. First of all, they want you to explain what is meant by a transverse wave. So first of all, what is a wave? So a wave transfers energy. So that's one thing. And then transverse wave, the vibrations or oscillations. You need to have these words in, one of these two. And these vibrations and oscillations are at right angles. Sorry about my writing. To the direction of wave travel. Sorry about my big writing. I'm not used to using the Apple Pencil, and if I put it on the pen mode, it's actually messier. So I'm putting it on the highlighter mode, and it seems to write more neatly for me. Okay, so oscillations is a key term. So you've got to have oscillations that accept vibrations. You need to have at right angles. So the vibrations are at right angles to the direction of wave travel. Or wave energy transfer, okay? So wave transfer energy and in transverse waves are at right angles to. What are the other ones called? Longitudinal waves, they are the vibrations are in the same direction as the direction of, or the backwards and forwards in parallel to the direction of wave travel. Okay, now here it says the student directed monochromatic light, single frequency, that means wavelength, onto a diffraction grating. There's a diffraction grating, and obviously it produces diffraction patterns, series of maxima on a screen a distance L from the grating. Okay, so once you know the distance L and you know the X, you can work out theta. You need theta because n lambda equals d sine theta. Okay, so this is the equation you're going to use. It's provided on the datasheet. So in these videos I use yellow as highlighter, and then I do the answers normally handwritten, but because I don't have the scanner with me, I'm at home, I've decided to just do it directly onto the paper, so it's done before the weekend's out. Okay, so remember, if you find these videos useful, please share them, because we're now well into 1,200, 1,300 subscribers, and to keep the channel viable, we need to increase our numbers. So the feedback is generally very positive. Now, the distance between the central maxima was measured as x. Yes, so x and L need to be measured when you do this experiment. This is a core practical. Yeah, and in this case, they've given you the wavelength, and they want you to calculate the number of lines per millimeter. Okay, now that's not d. Okay, number of lines per meter, 1 over d, will be equal to the number of lines per meter. And then, of course, if they want it per millimeter, they're just seeing if you can change units without getting confused. All right, so let's see if I can do this neatly on my iPad. Okay, so the first thing is you need to use n lambda. Now, because we are talking about the first order maxima, that means n is 1, okay? So the data is provided, we first need to find sine theta. So sine theta, first we need to find theta. So theta is from tan, because it's opposite, x is opposite the angle, and L is the adjacent. So tan theta equals 0.22 divided by 1.30, okay, 2 decimal places. That follows that theta, if you do tan to the minus 1 of that fraction, you will get theta equal to 9.61 degrees. For now, we'll keep it as 3 significant figures to be more accurate in our next one. Now we want to use n lambda equals d sine theta to find d. So it follows that d, because we want to do 1 over d, so in the equation we're going to get d. d is equal to n lambda, so it's 1 times 650 nanometers, and don't forget the nano means times 10 to the minus 9. Nano is 10 to the minus 9, okay, divided by the sine theta, so that'd be sine of 9.61, yeah, and when you do that, you get an answer where d is equal to 3.89 times 10 to the minus 6 meters. Okay, that's how many, that's the distance between two gaps in the diffraction grating, 2 slits. Okay, the distance between 2 slits. Now, we want to know how many lines per millimeter. So if we do 1 over d, that will be how many lines per meter. So 1 over d will be equal to 1 over 3.89. 0.89 times 10 to the minus 6, and that gives you that you're going to get about 257,000 lines per meter. So that's going to be approximately, so 2,507, and of course not exact, but that's for 3 significant figures like we did here. So that's going to be approximately 257 lines per millimeter. That's how many lines they managed to fit into that. And you can probably round it up to 260, lines per millimeter already given to you in the units. That's 2 significant figures. And that will finish off this question. Go from 3 to 2 significant figures. Hope that makes sense. So you're going to get marks for tan theta, presumably. You're going to get a mark for using n lambda equals d sine theta, so the numbers in. 1 for working out the answer, 1 for inversing it and rounding it up. All right, so it hasn't finished this question. It then says, explain how a first order maximum is produced. How is it produced? Well, first order maximum means that all the waves are in phase. If they're in phase, you get constructive interference. These are my notes. You have to put them into a clarity for the examiner. Constructive interference occurs, and this happens when you then need to mention that the path difference between the waves from different slits are equal to lambda. So if the path difference between adjacent slits are equal to lambda, then you're going to get the first position where you get constructive interference. Okay? So I think that's what you get. If n was 2, the first order, so this is n equals 1 here, first order. So if we were talking about the second order, n would equal 2, it means that the path difference would be such that still be in phase, still produce constructive interference, but this time for the second bright fringe, the path difference would be greater. Path difference would be equal to 2 lambda. And for n equals 3, what would happen? The path difference would be equal to 3 lambda. And that's why you get certain positions where it happens that all the waves from the adjacent slits, have the correct path difference to allow the bright fringes to occur. All right, so this is question 14. And now we can have a look at the mark scheme, parts A and B, how you do the tan theta, then working out D, and then inversing it to get them per millimeter. And they're just checking that you don't get confused with the units. All right? So you could actually make an equation where you can actually change n lambda equals d sine theta to do 1 over d. So if you did 1 over d, you could have come up with a new equation which will give you the answer directly to get to what they wanted. Okay, and there we go. For 14b part 2, they must be in phase. Constructive interference occurs, what causes the brightness maximum, and the path difference. These are the key terms. Linking all those 3 terms will get you the marks. Okay, the next question we did in part 1, so go back and find it in the same playlist. So question 15 we did, it was on electricity, so all the electricity questions are already done. Okay, remember, if you're my students, then I've divided this into the electricity in the first part for the practice exam I gave you, and now I'm going through the waves questions. All right, so question 15 is done. Question 16 is also electricity. So we did this in part 1 of the videos. And we're now looking for question 17, which is another core practical that you need to be familiar with. It's the vibrating string experiment. Okay, so the student investigated stationary waves on a vibrating string. Okay, so you should have done this in your own school. So this is a core practical. I can't remember the numbers anymore because I've done modular and linear and I get confused. So the mass hanger is used to control the tension, yeah, and the waves on a string, the velocity of waves on a string is directly proportional to the square root of tension divided by the type of string, the mass per unit length of the string. That's what the Greek letter mu stands for. Okay, so the student adjusted the frequency of the vibration generator, so it's got a frequency control on it, until the standing wave shown was created. So this standing wave is the fundamental frequency. And this is the frequency of excitation for this string, for this fixed amount of tension. So the tension and the length determine which frequencies will create this high amplitude. So the fundamental frequency, you get a high amplitude only at a particular frequency. So it's a type of resonance, and you need to know about resonance when you get into year 13 as well. So first of all, they want you to label each node, letter N. So there's a node at each end. Node means no displacement. So the displacement is controlled because it's over here and over here between these two fixed points. So nodes are positions of fixed points, or low amplitude or zero amplitude. And then in between you have an antinode, the opposite of a node, where you have maximum displacement. Remember that the center is zero displacement, so you have the maximum displacement in the middle, and that's where the amplitude is high, but only at the correct frequency. So you've got to find the resonant frequency, we call it. Explain how a standing wave is formed. Okay, so the way it's formed, I'm going to speak it. You're going to have to listen and change my audio into words. Okay, so the vibrations of a specific frequency, yeah, so it's controlled by the vibration generator. Remember, the student adjusted the frequency until high amplitude was seen in the middle, and you've got to go just change it slowly around where you notice that the pattern is forming. If you go away from it, the amplitude dies down. So we have vibrations. We want vibrations in there. So the vibrations are a wave, and the wave travels along the string, yeah? And what does it do? You then need to say it reflects. Where does it reflect? At the other end. So you've got the original wave and the reflection at the other end, so it's going to reflect, yeah, at the other node, the point of the other node. So it's going to reflect, so you're going to have interference or superposition of two waves. Yeah, the original and the reflected. Now obviously they're the same wave, just bouncing back, so it's an echo, the reflection. So the other end, and the where they go through each other, in the middle, where they are in phase, yeah, they reflect and they superpose. So you get 1 marks for talking about the reflection. Let's see what the mark scheme says. So the reflection is key, yeah. The vibrations travel, so obviously you have to have vibrations or wave travels, yeah, to the other end and reflect the pulley end, and when they go through each other, they travel through each other. they're going to interfere or superpose. Okay, so 1 mark for that, 1 mark for that. Yeah, I think that's actually the 3 marks. One from the fixed end and the other, so it's the 2 waves interfering. Yeah, I think it's a little bit of an easy question. I would have said where the 2 waves travel through, you get constructive interference. I would put that anyway, because the next examiner may be a little bit more fussy. Constructive interference equals high amplitude. So that will be the antinode. So I think they should have made this a little bit more details. Okay, so I've already told you everything else you need to know about the theory. I'm going to go straight to the mark scheme because it's a long question. Okay, so let's see what they're giving marks for. The waves reflect from the other end of the string and superpose. It's a very simplified version of what causes it. Okay, so the next one we're going to use the equation I showed you, yeah, in part C. So the student added masses to the hanger to vary the tension. So the tension is what? The independent variable. He then adjusted the frequency until he got the pattern that we showed with a node at each end, an antinode in the middle, and that was going up and down. And he recorded the tension and the corresponding values of F. So F for the fundamental resonance. So it's a fundamental frequency for each of the tensions. So if you change the tension, you change the fundamental frequency. Okay, so basically the fundamental frequency is the dependent variable, and he said the student repeated this procedure for number of tensions, so probably minimum of 5 to get a good experiment. And obviously they're telling you that what mu stands for, mass per unit length. And then the student plotted a graph of F squared against T, and it should get a straight line. And you've got to explain why that gives you a straight line. Okay? And the gradient will be 1 over 4 length squared mu. So how do you do this? Well, we know the equation provided is V equals the square root of the tension divided by mu, and mu is constant, so it's not changing. We also know that V equals F lambda, yeah? And we know that the length between the 2 nodes can be measured, yeah? And it's also constant. So that length that you can see is just got 1 peak or 1 trough. So the length is half a wavelength, yeah? The length is lambda over 2. Therefore, lambda is 2L, yeah? So lambda is 2L. So you can now change, you can substitute for V, make that F lambda equals the square root of T over mu. And for lambda, you can then say, well, F equals, because we want F on the y-axis, so we're going to put F as subject to the equation, and then we're going to square it. So F, instead of lambda, I'm going to put 2L. So take 2L on the other side, 1 over 2L, square root of T over mu, square both sides. It follows that F squared equals 1 over 2 squared, 4L squared, and then you get rid of the square root sign. Now you can see if you put this y equals m, everything in front of what you put on the x-axis. If you put on the x-axis t and you put f squared on y, then what's left in front of the x value will be the gradient. And that shows that you know how to analyze straight line equations, whatever you get. So you'll get, let's have a look on the mark scheme, we'll have a look at it later. So you get 1 for being able to do, so being able to link all that will get you at least 1 mark, I should imagine. 1 mark for getting the square root sign, I would say that, and 1 mark for linking it with that and saying that the gradient is 1 over 4L squared mu. Okay? Okay, hope that makes sense. Yes. Equating, it says equating f lambda with the TU is 1 mark. Making sure you know lambda is 2L, 1 mark, and then comparing it y equals mx plus c is 1 mark. So you get 1 mark for equating lambda with length. Okay? Otherwise you couldn't prove their equation. All right, so that's 17. And here's the results. They want you to now work out mu. Okay, so you've got to use the equation they've given you, and you've got to use the, you've got to work out the gradient. And I think they've done it in the mark scheme at 4.7, 2,500. So where the 2,500 line is, they've done it there. So then what you should do is you should show that delta y equals 2,500 minus 0, which obviously is 2,500 because it's going through the origin. And then over here, delta x is equal to 4.7, yeah, which is this point here. 4.7, the point where it crosses. Again, it goes through the origin, so minus 0, so it's equal to 4.7. That allows you to work out that m is 2,500 divided by 4.7. And whatever number that comes up to is 532. There's your gradient. You could put frequency hertz squared newtons to the -1 if you want to. I don't think they'll be fussy on that. Okay, so once you know the gradient, you then have to equate it to what we proved on the previous page. Yeah, so therefore m will be equal to 1 over 4L squared. Have a look at what we just wrote on the previous part, over mu. So you can just swap the mu and the m around. So mu will be equal to 1 over 4 times L squared, which they've given you, 0.85 squared, times m, 532. And when you get that, you get the mass per unit length. And that comes to mu as being 6.5. Is 6.50, so I'm going to just go straight to two significant figures, times 10 to the -4 kilograms per meter. So it's kind of, the mass per unit length is kind of way of working out how thick the string is. If you use a thicker string, it will change the fundamental frequency. So that you should give to two significant figures, and I hope you can read my writing. So that's question 17 done. Here's the mark scheme. We went through part A and B already, part C and part D. Okay, so you can see here they've shown it to three significant figures first in their calculation, and then they, as long as you get the gradient accurate to two significant figures in that range, depending on how you did your gradient, yeah, then you will get the third mark for accuracy. Accuracy means how close to the accepted value are you. Okay, one more question. Two more questions to go in this run through. Optical fibers can be used to transfer data, so they tell you that. One optical fiber is made from glass, so that has a N value of 1.5. Okay, that's going to be, and air is always 1.0, probably 1.00 to three significant figures. And they want you to calculate from the ray diagram the angle that it refracts it. Okay, now be careful. you need to know the angle of incidence and the angle of refraction. So when you do that, always show that you know that you're measuring to the normal. Okay, so when you're doing your normal, always draw it. This ruler doesn't let me do a dotted line, but this line should be dotted, so that yellow line is the normal. Okay, I'm not going to change it, so the yellow line is normal, and then the ray will bend towards the normal. That's not good. Let me do it again. I think because I used two motions. So we want the ray going in and bending towards the normal. Yeah, so it's going to come out around there. Of course, the continuation. So we want this angle, theta 2. Now you've got to use this angle, theta 1. So they're trying to trick you by showing you this angle here. Okay, that's not neat. Get rid of that. So they want you to make sure that you don't get confused. So the equation then is equal to n1 sine theta 1, that's in the air, equals n2 sine theta 2. So we know n1, we know sine theta 1, we know n2, yeah? So you've got to work out sine theta 2. So sine theta 2 equals n1, which is 1.0, times sine, not of 50, sine 40, and you divide that by n2, which they've given you, 1.5. Okay, so you put that in and you will work out that theta 2 is equal to 25.4 degrees, 3 significant figures, and you can round it up to 2 significant figures. And you get marks for what? Using the equation, yeah, working out theta 2, and it's another long question. So you get 1 mark for, oh yeah, so 1 mark for working out theta 1 is 40 degrees. Yeah, so 1 mark for that. So that's your 3 marks. So part 2, now they got the light inside the glass. So it's now inside the denser core of the fiber optics. Shows a ray of light inside the optical fiber. And then the air is on the other side. Deduce whether the ray will totally internally reflect. Okay, so obviously we still know the n values, 1.5 and 1.0, so you're going to use the same equation again. So this time n1 is in the glass. Sine theta 1 is 45 degrees. Now you will notice that they haven't drawn the normal again. So when you're drawing the normal, this time you want to draw the normal here. I've drawn it in yellow just because it's fainter. So again, theta 1, as it happens, that's theta 1, which happens to be 45 degrees. So be careful. Don't use the angle to the boundary. Okay, in this case it's the same. Then n2 is air and sine theta 2. Yeah. So you want to know if it's totally internally reflected. Okay. Now totally internally reflected means that it will happen when sine theta 2 equals 1. Yeah. Because it will go along the boundary. Okay, so what is that you want to find out? What is the critical angle? Okay, so it will totally internally reflect when the angle theta 1 will be greater than sine c, will be greater than c. Okay, maybe I shouldn't put that. Okay, so when you get sine theta 2 is greater than 1. So the way I would do it is to explain that sine C, when you got 2, sine C is equal to n2 over n1 always. Now we know that n2 is 1, so it's going to be 1 divided by 1.5. That will give you C of 40, oh my god, I can't write, 41.8 degrees. And since theta 1 is greater than C, it follows that total internal reflection occurs. Okay, so you get 1 mark for using sine C equation, 1 mark for working out sine C, and 1 mark for saying that it's greater than, therefore it will totally internally reflect. All right, now this bit. It says data is transmitted along the optical fiber by pulses of light. Okay, now I've shown you pulse has a duration of time t, and the intensity is constant when it goes in. Okay, now but the light in the pulse can take different paths along the optical fiber depending on the thickness of the fiber. The diagram shows 3 possible paths. Yeah, so you can see 1 is refracted and exiting the side of the fiber, and 1 is going straight through, yeah, and 1 is zigzagging through. Okay, so explain how the intensity and duration of the pulse of light leaving the fiber are different. Yeah, so light leaving is different from the pulse that entered the fiber. Okay, so when it enters, obviously the pulse will be of a fixed duration, but because you got different distances, that each of the rays travels a different distance. Yeah, so you got to mention the light rays, so that let's do it in blue. The rays travel different lengths or distances. That means if they're traveling different distances, they take different amounts of time. So that obviously that's going to affect, that will lengthen the pulse time. Okay, so if they take longer to travel, further to travel, they'll take longer to travel. The different rays take different amounts of time to exit, so the pulse will become broadened. So what we call pulse will be broadened. So obviously you don't want that, okay? And there are ways to try to control that. And then now about the fact that, let's do this second bit. And again, because they're traveling, some rays enter at different angles. Yeah, I'm just put theta for short, you can change it. Some may refract, as shown here. Yeah, out of the side, ... so you can change that. So you will lose some light. And therefore, if you lose some light, the intensity will decrease. The intensity of light exiting. So you've got to put all of these 5 points into your answer to get the 5 marks. These are the crucial things. They travel different distances, they take different times. That means that some rays will arrive before the other. Obviously that common sense will tell you that the pulse time will be broader, and some rays will also arrive at different times. So the intensity will be over a bigger time. Therefore, the intensity will also be over a wider area. And because you lose some, the intensity will also decrease. Okay? So sometimes what they do with the core, which they're using, in this case, the glass is the core, they use a different material on the outside of the glass. Okay, they use a thin layer of another transparent material and they call it cladding. Okay, the transparent material has a lower refractive index than the glass, has to, otherwise it will lose a lot of light from the sides. But it's more than it was with air. Okay, so N of the cladding is greater than N for air. Okay, explain how the cladding affects the critical angle. Okay, so remember, sine C will be equal to N2 divided by N1. N1 is the core glass. So say it's 1.3 divided by 1.5. So you can see sine C goes less. So if sine C goes less, so because N2 is now greater than N for air, so therefore sine C increases, therefore the critical angle, so sine C decreases, yeah? Sine C is a smaller fraction, yeah, it's a bigger fraction, sorry. Sine C is increasing, yeah? N2 to N1, yes, I'm just making sure I'm not confusing myself. There's a smaller difference in the refractive indices is basically what you've got to say, which I've shown here. Yeah. So the sine C will be greater, therefore C will be increased. And if that happens, it will change the behavior of the fiber optic cable. Yeah. So in other words, there will be some angles which will not be greater than the increased C, and some of it will refract out, and that actually reduces the broadening of the pulse, believe it or not. Now you don't need that for this question, so I hope I didn't confuse you in my explanation there. So with the cladding, the ratio of the refractive indices decreases. Yeah, so the sine angle, so the cladding N2 to N1 decreases. Oh, I got it the wrong way around, haven't I? N2 to N1 increases the ratio. Yeah, the ratio decreases, yeah? The value of sine C is a bigger fraction, okay? So C is increased. I did confuse you, I'm sorry. So this can help with the dispersion of light along the fiber optic length. Anyway, have a look at the mark schemes to see the wording, because you can get confused when you're talking at the same time. So, the wording for the final part we'll come to. This is the first two parts if you want to stop the video. Okay. Part C, the broadening of the pulse and the intensity loss. So here, let's just go exactly through that wording. There is a smaller difference in the refractive indices. Yeah. Or you could say there is a smaller difference in the speed of light between the two materials, which is true. Or you can say the cladding has a greater refractive index than air, which I mentioned. Or the cladding has a refractive index which is greater than 1 because air is 1, so these are the same point. So the ultimate point is that the critical angle is increased. But they then haven't said, well, how will that affect, how will that affect this question? And that will be like a part E, but they haven't included it. And I know the AQA exam like to look at different types of dispersion of light through fiber optics. Okay, I think this is the last question that we haven't been through in the run-through. Question 19. So question 19 is about the photoelectric effect. So the scientists used a photocell to investigate the photoelectric effect. So here you've got the metal plate, and light incident on the metal plate causes a photoelectric effect. So if you have light coming in, say, of red light, say if red light comes in, photon of red light, and a photon of green light, and a photon of blue light. The blue light has the bigger frequency, yeah? And if the frequency is high enough, then it can give you energy equal to HF. So if the energy is greater than the work function of the metal, then photons will release electrons from the metal plate. Okay? Remember that the energy is to do with that. All right, so, and then if they get to the electrode, you're going to see that they can measure the current. So it says the beam of electrons, the beam of the light, monochromatic, so single wavelength, is directed onto a metal plate and causes the photoelectric effect. Therefore, because it's monochromatic, it's a single frequency, all photons have the same energy, depending on which color or which frequency they use. That's the frequency, that's the energy. And then you've got to explain why the beam produces, if they all got the same photon energy, why do you come up with a range of kinetic energies? Okay, so not all the electrons are at the surface. That's the first thing you need to know. Yeah, so not all electrons are at the surface. So how do you do this question? Is you've got to think, okay, if they're not all at the surface, the ones at the surface will get most of the excess energy needed for kinetic energy, okay? Because the equation is HF input, photon energy, equals a minimum energy required to get to the surface, and any leftover energy becomes kinetic energy of emitted electrons. So you've got to put these, what I'm saying, into words, okay? So I'm not going to write everything down, but you've got to say electrons is a key word. In the metal can each absorb. So each electron can absorb one photon. That's what they like you to say. So each electron can absorb one photon. All right. Different electrons need different amounts of energy to escape. Yeah? So the minimum energy are the ones at the surface. So the photon energy, because the photon energy to get to the surface of the metal, and the rest of the energy, leftover energy, goes to kinetic energy. So basically those are the 3 points you've got to clearly state in to get the 3 marks, each of those lines. And you can have a look at the mark scheme on the wording. Okay, hope that makes sense. They then are connecting the photocell to an ammeter and a battery. Okay, now they put the positive here and the negative here. Positive is a big line. So obviously here's the metal. The metal is here. So the photoelectrons will be attracted to the electrode because it's positive in this first case. Okay? In the next part of the question, they're going to make it negative to actually stop them, prevent them from reaching. The scientists directed different frequencies and intensities onto the photocell. When they did it with white light, it caused no current. When they did it with white light with a higher intensity, it caused no current. Okay? So the intensity makes no difference. But when they did ultraviolet light, which has a higher frequency, even with a low intensity, it caused the current. So intensity is not key, frequency is crucial. Now this is a 5 marker, and they want you to explain that these are how these observations show that the nature of light is not so much a wave in these observations. It's not supported by the wave theory, but it is supported, yeah? It is supported by the particle theory. So it's the dual nature of light. So it's duality. That we have 2 theories, okay? So how are you going to break this down into the 5 marks? So first part is about intensity doesn't seem to make a difference. Now, if it was a wave, so first of all, the wave model. The wave model just would suggest, the wave model would suggest that if you increase the intensity, is proportional to the energy. Okay? But of course, even with increased intensity, there was no current. And no current equals no electrons emitted. Yeah? So with the wave model, the increased intensity should lead to electron emission. Okay? Eventually, if you wait long enough. So in the wave model, more intensity means more amplitude. So you also want to maybe mention amplitude, because amplitude is linked with energy. But even with more amplitude, you don't get emission. However, in the particle model, if you look at the particle model, the intensity means, when you increase the intensity, more electrons per second. But that doesn't mean that they will emit electrons unless each photon has sufficient energy. Remember, one photon can release 1 electron, can give its energy to 1 electron. So, however, in a particle model of light, more intensity means more photons arriving per second, but does not increase the energy of each individual. Okay? So, intensity equals more electrons, but no emission unless each photon has sufficient energy, because photon energy is related directly proportional to the frequency. Yeah? But, so if you increase the frequency goes up, then photon energy increases as per the equation, above a certain threshold, F0 we could call it, and this leads to emission. And the latter is observed, so therefore, because we observe when you increase the frequency, emissions of electrons, this supports these observations. Support the particle model. Sorry about my big writing, but I hope you get the point. And those are the 5 points you need to look at. Okay? So there we go, 19A and B. These are the 5 points we just looked at. They may have the keywords that you want to stop the video and see if you've got it. Okay? So you should mention the ultraviolet being higher frequency. Okay? I might have missed that out, but basically the photons with enough frequency are crucial. So in here we should mention UV, frequency goes up, therefore photon energy goes up. So we need to relate it to the observations. Okay, so I might have lost 1 mark. Part C, which I think is the final part. Part C is scientists reverse the connections of the battery, so now they put the negative at the top. So obviously it's going to repel the electrons. The battery has negligible internal resistance, so you can ignore that. When the photons have enough kinetic energy to overcome the negative potential difference across the photo cells, which is the energy to overcome is 1.5 electron volts of energy. Yeah, remember 1.5 volts on electrons is 1.5 volts of electron energy. And if the ultraviolet has a wavelength of 250 nanometers, yeah, remember that's 250 times 10 to the minus 9, then you can work out whether there is a current in the circuit, and they've given you the work function, which is equal to phi. Okay, so how do you do this question? You know that HF, the incoming frequency, so you can work out frequency equals C over lambda, yeah? So you can work it out that way. So HF must equal the minimum amount of the work function plus, and the rest will be the KE, yeah, that is left. Now, if the KE left, after you've taken the work function off, is correct, then you can work out the kinetic energy. Come in. Kinetic energy is maximum. You can then work out the frequency minus the work function, and that will allow you to do the equation. Sorry about the delay, I just had to open the door. Okay, so the frequency you have to work out from the wave equation, and the frequency when you work it out will be, so the frequency there, if you work out 3 times 10 to the 8 minus, divided by the wavelength, you get 1.2, yeah, times 10 to the 15 hertz. Okay, so you get 1 mark for doing that. Then you can put in the value in HF. So you multiply HF together, and that will give you, hang on, let's do it properly. So HF is going to be equal to 6.63 times 10 to the minus 34. Multiplied by this frequency, 1.2 times 10 to the 15. And then you take away the amount given for the work function, which is in the question, minus 6.9 times 10 to the minus 19. And when you do that, the remaining energy for the kinetic energy that you get, the maximum, that will be because the work function is the minimum, so it's the electrons that get the most kinetic energy. It comes to 1.06 times 10 to the minus 19 joules, where you can see that that's going to be too little because it's not even 1 electron volt. How do I know? Because to get the kinetic energy into electron volts, you've got to divide that 1.06. You've got to divide that 1.06 times 10 to the minus 19. You've got to divide by the charge of an electron, which is 1.6 times 10 to the minus 19. So you can see it's a fraction of the 1 electron volt. So when you do that, you can see that this cancels out. So it's going to be approximately 0.7 electron volts. And obviously this is less than the 1.5 electron volts needed. So no current will be detected. And that's how you get the marks. Okay, so the first mark is use of this to get the frequency, use of HF to get the energy in joules, take away from the work function, another mark, that's 3, work out, convert the kinetic energy into electron volts, and then show that it's 0.7 is less than 1.5 electron volts, so you get no current. And that is the end of this second part of the run-through. Hope you found that useful. Don't forget, share, like, subscribe as normal, and I'll catch you in the next video. Bye for now.